The first 3 weeks of the eruption here in Hawaii, crazy things would happen in the middle of the night. A new fissure would open up and it would threaten a new neighborhood. Thousands of people are evacuated from their homes. I started the Hawaii Tracker Facebook group to help people understand what's going on and get their questions answered.
Hey, how's it going? We're live. This is Fissure 20.
We had hundreds of people all throughout the neighborhoods sending in videos, articles, and images. We spend a lot of time making sure the accurate information gets out.
This is live. There's still lava moving.
They weren't just sharing a story, they were helping their neighbor. If a family was being evacuated, a group would just jump in and help out. So it was huge. They were watching out for each other.
Hello everybody, thank you for coming. Thank you for the support from everybody.
As we go through this, we're growing closer together as a community. When tragedies like this strike, you really realize how much you need each other. As a community, when tragedies like this strike, you really realize how much you need.
Aloha everyone, I'm geologist Philip Ong, here with Mr. Dane DuPont of HawaiiTracker.com, bringing you guys another Kīlauea volcano update today. And as a special bonus, we're going to spend quite a bit of time today watching the USGS presentations from Volcano Awareness Month, the first 5 that have been released in the first half of the month. Dane will be collecting questions about current activity as well as about the presentations, so make sure to get them in early today. We're going to talk activity up front here and fairly quickly, quicker than usual, before we switch over to presentations, and let them know if you have any issues with our audio or video or anything like that as well. All right, so in brief, what's happened over the last week has been 2 more pauses in the volcano, each lasting about a day, and you guys are seeing here a loop of the most recent one that was a couple of days ago from the S1 camera from the south, USGS camera there. And a little bit shorter pauses than the ones last week, so 2 one-day pauses, and each time the lava has burst back forth from that same west vent area. You guys can see at the top of that image looking right there. And the pattern of eruption and pauses is still mirroring the ground tilt, which is a proxy for the pressure, how much pressure is in the volcano. So when a pressure is rising and lava is bursting out, when a pressure subsides temporarily in a cyclic pattern there, then it seems to be pausing and just goes back and forth and back and forth. So twice in this past week has been fairly similar to the last few weeks. No big news there. The more unusual thing that's happened in the last week has been a flurry of small earthquakes at the base of the volcano, down 10, 14 kilometers down. This is down below any of the magma reservoirs that we talk about around the caldera. So down at the base of the volcano against the old, against, I mean, it's probably close to the mantle boundary, in fact, press down there. We'll look at that a little bit as well, but no effect of those earthquakes on the volcano. So let's get to it here, and let's advance from our S1 camera to our F1 thermal camera. And I'm going to play it here back from 1 week ago on the 6th. I'll play it, and I'll try to zoom in a little bit here so you guys can see the activity. There it is, crusting over, still active in this northern outlet point of the western vent. Turning over periodically there, and you still see some glow from the top of the west vent as well, right over here. And it bursts back out, and you can see that that's the most impressive time when lava bursts out, not just from the outlet, but it bursts out from the top of the vent, and all these various little streams that flow all around from this high ground down into the edges of the crater here and into the... Here's a second one. This is now, I want to say January 10th to 11th, more or less, or 11th to 12th. And here comes the burst again. Similar, large, bunch of brightness coming around this west vent area right in here. So that's the camera. I think it's coming up to right around now here. Right up to our most recent frame, looking like that, right? So besides actually having lava in the lake, now that I've zoomed it back out, you can see that there's, go back a little bit. The lava is still going underneath this crusted over area, and it's popping up in these ooze outflows here on the north and over here in this downdrop block area. Quite a lot of lava filling that downdrop block area, having oozed out from beneath this crust over there somehow. Okay, same sequence from the last week, this time from the KW camera, the visible camera on the west rim of the volcano. A little bit more of the caldera there. See, there's that little bubbling point, west vent right in here, downdrop block reactivated. Same view as the thermal image, just in the visible range here. And it's been a fairly good weather week on the volcano the last week. Not a whole lot of bad data on the monitors, bad images in our time lapse. Nice to see that. And one last time lapse here. This is from the V1 camera, this camera that's kind of zoomed in. Rewind back here to this screen. So in this view, the KW camera, zoom it in here. We're zoomed into an area about like that in this image right. One camera is play up for the last week. You just see the edge of that north outlet right in here. This is the area that stays active, whereas this part of the lake is the one that's going to drain and harden over. That there, in the west vent, you can see it's got a small opening at the top and growing taller and growing narrower at the top as spatter comes up through. But that does reshape itself, it seems like every week, with one of these deflation-inflation. So when lava bursts up and back through, you see it essentially shatter that top, widen that opening. There you saw it happen right there. And then it builds it back up and closes it back up again to that smaller opening and taller profile there. See that happening as well here. That's the time lapses of what's happened in the last week. It's been pretty similar to what's happened in the previous few weeks, so I won't dwell too long on that. But let's look a little bit at the signals here. Here's our most current, let me refresh just to cover most current images. So there's our S1 camera, still looking very similar. The views we just showed you guys, and thermal image, still very similar. So outbreaks, northern and north side, downdrop block. But most of the activity in the lava lake, making good viewing from the Kīlauea overlook and Hawaii Volcano National Park still. A better week for viewing with only 2 days of pause. Still, it's been off and on. So them. All right, looking at the 1 week of data here, this top image is the summit lava depth. And it's interesting that it's now showing much more variation. Since somewhere right in here, it's not clear what exactly happened here. Seems like the spot on the lake that was being measured has changed its character, or the laser got moved to a slightly different spot, one way or the other. But on top is a lava depth, on bottom is our ground tilt. And you can see from about this point on, right in here, very similar shapes, right? You can see even these small little deflation-inflation events, more of these V-shaped ones showing up in the lava depth as well, here and here. The overall shape of the lava depth increase is looking more like that characteristic deflation-inflation shape as well. So very interesting to see that close of a connection, right? And this is similar to what we talked about last week and discussed from the 2008 to 18 lava lake. This is a plot from 2012 showing similarly lava lake level within that open pit that was fed from below. The ground tilt accordingly. Very similar, except that we're not having lava just rise and fall always visible in a pit. It's going out of sight and then into sight, out of sight and into sight. So fascinating to think about that and what that might mean for the long term. But we'll leave that for a future time. Let's look at the month-long patterns. And here on top, once again, is a lava depth. You can see that previous to this change last week, right in here, we did see some indications of these pulses, right? But they were much smaller here, on a range of, looks like about 2-3 meters or so, a little surge, and then coming back down and then flatten out, and a little surge, a few meters, and flattening out. Whereas now, with this one, we're ranging from, this is about 310 meters here above sea level, and down here it's about 297, we'll say. So we're looking at 13 meters, that's maybe 40 feet or so of filling and draining right there. So that makes me believe that this area is now measuring that main part of that canyon where the lava is refilling all the way and then draining back down. And previously it might have been more on the edge or on part of the edge that collapsed in, so now it's deeper or something like that must have been what's going on. That's the most likely explanation there. Compared to the month-long tilt here, you can see that now we have that correlation here in the last week, and before that there were certainly correlations, but it wasn't this one-to-one correspondence here. Interesting to note that there. As far as the gas is also mirroring the summit tilt. So during these high points, you have a lot of gas coming out, and during these low points, not a lot of gas coming out. So correspondingly, depending on when the measurements are taken, and see here the dates on the bottom, you either get a low value during a pause, or you'll get a high value during a reactivation there, or perhaps in here. So the last values here have been in a range of 3,000 tons per day or so, which is within a ballpark, nothing surprising there. And the low ones in a few hundreds as well. So similar to all other low points we've seen. Note that. That's still the pattern. And here is the interesting thing on our earthquake plot, right? Earthquakes per day is our measure on the left, and we're going up by 20, 40. This is 100 right here in the middle. And 100 is perhaps our threshold we'll talk about today, right? So we actually had on the 7th about 100, the 8th, 9th, and the 10th about 100. On the 11th we were up to 170. On the 12th back to 100, and today we're still climbing up. It's incomplete for the last day here, but you see this little, it was kind of a 1 hump and 2 hump of extra seismicity, and we're going to look at that next here. That comes from the bin that's plotted here on this map. So the earthquakes on this map are the ones that are being counted on the last plot. So there can be earthquakes in a Pahala cluster, which will be one of the topics of discussion in a seismology talk today by the USGS. But we're looking at in more detail these ones right here, right underneath the summit. They're all in this yellow range, which is between 5 and 13 kilometers down. Really, the majority of them are between 10 and 13, somewhere in that range here. But it's interesting to look at these plots not just in this map view, but we're going to scroll down here and look at, this is a depth versus time plot here, and it says 1 week as well. So the Pahala earthquakes are these blue ones over here. You plot on this map as this lower blue band, and you can see that there was some more active times and less active times and more active times. And in fact, when we looked at last week in our update, we saw that little bump in seismicity that corresponded to this time from right in here. And at that time we could say, okay, look at all the seismicities occurring here in this blue band, and really not so much happening up here in the top part. There. Now, since then, you can see this big yellow band taking over right through here, and with notable gaps down in the Pahala earthquake. The Pahala earthquakes are still happening, but they're not what's causing the signal to be overwhelming. What's causing those numbers of earthquakes, you can see very clearly, is right in here, this little band right in here. So hard to tell from the scale here because we only have like 10 kilometers, 20 kilometers down to see the resolution in here. So we'll look at more detail at the earthquake plots here. Seconds. We'll just finish off our monitoring signals here. Our GPS at the summit is maybe showing a little bit more extension, some slight extension, but very, very flat otherwise on average, right? And this variation we see through here is in part from deflation-inflation events. I don't know if you can see any of it. So a little bit of scatter through here from deflation-inflation events, but it looks like it might be on a slight rise. It's hard to tell right in there. It's not, certainly not skying up like it was doing prior to eruption before, so we're not expecting any major change. But it does show that the volcano is not like it's not popped out. It's not spent. There's plenty of magma in there. Like whatever's coming in has been able to get out. And when you start seeing it expand a little bit, that means that more may be coming in and is getting out. So that's what that might mean. So that's a slight indication of a robust and healthy magma supply still in the summit region. And in comparison, across Pu'o'o and the rift zone, we're still seeing a downward trend. That's a contraction across the rift zone, even in this most recent period here. So still quite a bit of scatter. Maybe this is something to do with the deflation-inflation events also. It's hard to tell. But overall, the downward trend right through there. No signs of activity on this rift zone. Okay, so looking at the earthquakes a little more closely, let's look at that. Here is the Iris earthquake browser, and I will animate these earthquakes for you guys. It can be a little bit hard to see them on here, but you can see they're east of the pit, right? This is the old topographic map right here, but you can see in this eastern part under the caldera. It makes it look like an extending to the south here as well, right? And it makes it look almost like it's related to the surface topography here, but you got to remember that this is all in the depths of 10 or more kilometers down. You're looking at 6 miles, so right, which is a long way down. So it doesn't directly associate with. It might be hard to tell, so I'm going to elaborate on that a little bit here. And first, what we did is took that Iris earthquake data. Scale here, but up here's a 0. 0's up here, and this is 5 kilometers down, 10 kilometers down, 15 kilometers down, right? So, and then this is time. This is a week ago, day after, and so on and so forth like that, right? See that in this 10 to 15 range, right in here, is where these earthquakes are happening in the shallow. I basically zoomed it in and changed the color, and you get so that's the first little flurry right through there, a little bit of a gap, and then a second flurry that occurs right through here. I wanted to zoom in so we could see if there was really any connection to any of these deeper earthquakes to some of these shallower ones up here. The shallow ones are more common. This is up in an area of the summit and rift zone reservoirs, so you expect that to happen up here. This is all way below that, and so but there's no connection from here going up, right? That's not what we see. So it may be magma coming into the base of the volcano, and if it's getting up from here to here, it's doing so without any earthquakes. And we're not seeing any huge inflationary signs like we just showed you guys in the tilt. Yes. But once again, this might be a sign of some adjustment down at the base of the volcano. That could have to do with magma coming into it, or it could have to do with the actual settling of the volcano as well, and maybe the combination of both. Adjusting forces there. So a couple quick cross sections here to remind you guys. And here's our summit caldera up here. Our 2 rift zones. Southwest rift is that wing. Southeast rift zone is this wing right over here. That goes down to in a range of, we'll call it 3 miles or so right through there, right? So we're looking down at, we'll call it 6 to 8 miles or so, like down, way down in here, somewhere in this region as it's drawn on this particular cross section. It's like down in this root underneath all this upper stuff, right? A couple other views. This is a view taken from examining the speed of earthquake waves as they travel through the rocks, and essentially the less dense and shallower they are, the slower it goes. I mean, still 3 kilometers per second near the surface, but down towards the base of the crust, it gets up to 6.8, and so you actually are able to draw some different velocity boundaries in there, right, as an approximation of different behaviors of the crust and the mantle there, right? So I scroll this over to the elevation now, and now we're back in kilometers. But we're looking at this range of 10, 15 to 13 or so, right in there, right? Notice this big black line right through there. And that's that boundary between crust and the mantle right here. There's a big jump, often known as the Mohorovicic discontinuity right here. As a seismic discontinuity, much denser rocks thought to represent the mantle rocks below. And then this low density stuff coming up through the middle is that plume, right? So some more interaction beneath the caldera, so near this plume area, but also you can imagine this is that lowest part of this bowl of the volcano that's pushing down. Imagine we're adding material up here and shifting the weight up above, and so you can imagine adjustments below, and either or both, it's not quite clear. We'll await the experts from the USGS to chime in on it. All right, and then one last one here. This is a plot that's taken from Wes Thalen, and I forget the second author now, but this will come up later in a Volcano Awareness Month talk as well. And the scale here in kilometers, 20, 40, 60. So we're looking at maybe halfway up to this upper bar here. So that puts us in the bottom of this blue zone right through here. So there's this area of increased seismicity at the base of the volcano here, and so that's what you're seeing right there. This is that whole. But there's thought to be, besides the magma pathways that come up, perhaps some that might come laterally from the Pahala zone as well, but that is also occurring below here. So if anyone wants to speculate that Pahala's got anything to do with this, then you could suggest that, well, the extra earthquakes in Pahala is a healthy supply coming through, and that's feeding all the way through into the base of the volcano, and it's got possibly other reservoir storage areas at different depths, perhaps, before it gets to that shallow point that we're talking about most of the time, as far as it affects our signals at the surface here. So we'll leave it at that there, and we'll revisit this with the USGS talk when we discuss Pahala earthquakes off to the side here. But one last thing is going to be the most recent map that's been put out by the USGS here. Map was released last week, but the data goes back to December the 30th, 1 p.m. Not a whole lot of change in the extent of the flows, but the numbers are something that I find always interesting. So the surface is up to 2667 feet above sea level, 813 meters. Thickness of 230 feet, 70 meters. That's in this most recent phase, right? The volume now 10.5 billion gallons, or 39.9, essentially 40 million cubic meters here. Not a whole lot of change in the lot of extent. At 40 million, we can plug that into our graphs and spreadsheets here. That puts our point right up here, right? The red curve is this eruption that began in September 2021, and the blue one began in December 2020. And the point here is that we have now, at the same timeline into the eruption, have now exceeded what the last eruption was doing, right? So the last eruption ended at 41.2. We're up to 39.9, so we're getting pretty close to exceeding the full volume for the entire eruption of the last eruption without having had the full duration of it yet. So stepping back a little bit here, you can see that we started off a little slower, still fast, but you can see that this more intermediate pace, right, is maybe sustained longer, and that's why we're seeing these lines cross right up here. And that's interesting in the future once again. In more detail, as far as the eruption rates in between these different map data points, we've both trailed off from our high values at the beginning, in the first week or so, weeks perhaps, crashing back down, and then really since this 2-month point right in here or so, we've been in both cases below this 5 cubic meters per second threshold. The red is what we have now. The most recent one might put us around very roughly estimated 2.4. But before that was 1.1. One before that was 2.6. So, you know, that's all with error right now. So maybe on average, you could say we're coming out maybe around 2 or so, something like that. Right? Which in comparison to the last eruption, we were down somewhere around 1.5 or just above 1 or so. So a little bit lower, right? Which is what we see reflected in the fact that we're catching up in total volume right now. All right, that's all the current volcano data we'll get into today. We can take some questions on this current data before we turn to all of the USGS presentations for Volcano Awareness Month, at least the ones so far in our first 2 weeks, which are going to be 4 of them, right? The first one is going to be Kīlauea erupts after more than 2 years, so it's a review of the eruption, these 2 eruptions. In fact, she'll discuss what these high values actually are. This is just an estimate from those maps that are put out, right? But she'll actually report the real data here and show her version of these graphs with the real data. And then we'll look at Olivine, the Olivine time capsule, like how it can extract time data from olivine crystals. We'll review the earthquakes with Ninfa Bennington. We'll have a short talk with Don Swanson about Kilauea's recent explosive history. And finally, Brett Carr will talk us through 3-dimensional mapping of Kilauea. This is the structure for motion that they've been making all the maps from, like this one I just showed you guys, how these maps are being produced, flying around in a helicopter, taking pictures, and then putting them in a software to create these maps, 3D maps. So pretty cool stuff there. We're going to let the USGS guys do the talking in the next section, but any questions for now, Dana, we can address in this?
Yeah, we got a couple. First, want to do a little thank yous and that kind of stuff. If you are here, we thank you for coming and checking us out. If you consider sharing, subscribing, that really does help with the algorithm, getting this kind of content seen by more people. Really does help us out. We don't have an advertising budget to do that. Otherwise, we rely on viewers like you to do that. We also do take donations on hawaiitracker.com/support, as well as the super chats. We did have a $35 super chat from our longtime supporter, Gary Bryan, who says, "Thanks for all your work producing these updates. Great job, Phil and Dane, and we appreciate it as always." If you are so inclined to make a donation, we also take those on hawaiitracker.com/support. We have a couple of supporters that we want to acknowledge. First one being Kaleo's Bar and Grill in the heart of Pahala. They have a new establishment in Orchid Land, and they have 2 different menus there. They have some traditional dishes with some more local twists on them, indoor, outdoor dining options, takeout options, all that kind of stuff. They have a full bar. Definitely a place to check out if you're out in Puna and need a place to eat, or out here just visiting. Definitely a place to check out. So we thank Kaleo's. And the second one is Kalani Tours. Kalani Tours does a variety of different kind of tours. Definitely talk to them if you're coming out and looking to get around the island and see the sights. They do some Kona Coffee Farm tours, some waterfall tours, but as long as that volcano is going, probably that lava tour is the spot. Go around Hale Maumau in a more private group, so you get all your questions answered. We definitely thank Kalani Tours for being a sponsor. All right. I think that gets us through that part. We can get into some questions now. First one was about what somebody was asking about the depth of the lava lake, the readout, and what do you think's going on with that?
Well, yeah, that's why I did cover that there, right? I think that's
okay.
I can be more specific here. So let me pull up the
little depth graph
here, right? Well, yeah. So the depth graph. So here's probably the main thing to consider is that when you look at this is not the angle that the laser rangefinder is pointing at the lake, but it's being shot at to a point somewhere near the west vent, right? So the west vent's right over here, and it used to be pouring right into the lake. Right, the edge of the lake used to be right over here, there. So it was pointing off somewhere in an area over very roughly right in here. We'd have to look at the talks by Matt Patrick and Carolyn to really remember exactly where, but it's more or less in this area right in here. And I think it's pretty close to this edge, right, is basically what it comes down to. So I think that before, about a week ago, the laser was shooting onto maybe the edge or the inner edge, right, maybe where it's still dropping a couple meters or so when it's receding. But since then, maybe this edge has maybe dropped deeper, maybe a part of the cliff fell off or something, or the laser is pointing slightly off to the side where it's pointing more into this deep part right in here. So now you're seeing, because of the lava lake, when it's draining out that it's really about 40 feet or more, right? That you're seeing, right? That 13 meters. is the real difference in how much of the lava is dropping and rising and within that canyon. But if you're only pointing to the very edge of the lake, you might only see it coming up and down 1 meter, and then you won't see it ever drain because it's basically not filling, it just becomes flat. And so if I pull up, let me go back to that here and back to that. Here it is, the lava depth. Look at the month one right here. So it looks like if you're next to the edge here, the lava is coming over the edge, and maybe it's pushing it up a little bit, bulging up the whole area, and then it's basically settling back down. And here's our flat. Right, the thing is never really draining at any point. You don't really see much of this downward. Right? Maybe earlier you saw some of that, but like I've said, the configuration is changing over time. So I think it basically is pointing somewhere that now is able to drain all the way deeper. So now you're seeing this full breadth of what's really happening, whereas before you were getting kind of the edge effect. That's my best educated guess. This signal right in here is interesting. So that could be when that either cliff collapse, or you're pointing at something and then suddenly you're pointing at something that's a lot lower, right? So it dropped down, maybe that edge of that shelf collapsed right there, and then you're seeing a lava fillet and lava drain back down to that low level where it collapsed to down there. That's my best guess.
All right. Thanks for going over that again. We did have one more question that was about the recent seismic activity. Richard asks, is that seismic activity what looks to be causing the lava lake some changes in the lava lake involving settling?
So I should have mentioned when I was talking about these earthquakes under the summit, and I'm pulling up here the other USGS map. These earthquakes. Should have mentioned here, let's sort this by largest magnitude. The largest magnitude was a 2.4, 2.3, 2.2, 1, only one of each of those. 2 2.0s. So most of these are under magnitude 2. Huge majority of them are very, very small, getting down to 0.6s. These are very small earthquakes, and they're happening 6 miles away from the lava lake. Through a huge stack of rock, right? So I don't think that the earthquakes are big enough to disturb that surface area right up there. I think it's more likely the filling and draining of the lava lake, and then you're supporting the wall and unsupporting the wall, and it might cause those little cliffs to collapse, or that settling and that kind of draining. And that you see that because those cliffs are so tall when the lava drains away, you really see the shadows appear really well on the time-lapse cameras, and that's what I would expect is what looks like the settling, right? Is that area, is that effect of the more so than they're actually changing the ground.
All right. Well, I think that does it for Q&A, so we can get into some Volcano Awareness Month stuff.
All right, sounds good. So yeah, we'll switch gears here, and let me put up on screen here. This is the USGS Volcano Awareness Month virtual program. So these are all being released. If you have already studied all these and watched them before, feel free to just skip ahead if you want to hear any of our commentary afterwards, or watch them again and see if I pick something else up this next time around here. But you can see this is a whole month of programs being released on Tuesdays, Wednesdays, and Thursdays. And so here we are today on the 13th, and so we'll watch all these videos, 1, 2, 3, 4, 5 here, right? And 2 of them are a little bit longer in the range of 15 minutes or so, and the other ones are shorter, 5 minutes or less. And we'll start with this one is Dr. Carolyn Parchetta. Kilauea erupts after more than 2 years of quiet, twice. So let me change our view here, and we'll let Dr. Parchetta take it away here for the next 14 minutes. And feel free to type in your questions as we go along, and if there is a question that pops up, we may pause it and discuss a little bit, or rewind, that kind of thing. Otherwise, we'll play through until the break here and then come back to you. All right, so we'll be right back. Passing it over to Dr. Parchetta.
Hi, and welcome to Volcano Awareness Month with the Hawaiian Volcano Observatory. My name is Carolyn Parchetta, and I'll be giving the first presentation of the month on behalf of the entire geology staff at HVO. Today we're going to talk about the 2 eruptions we had in 2021, which follows a 2¼ year quiescence at the volcano of no eruptive activity. So let's jump right in. This is going to be a 10-minute style talk. This is not a 45-minute in-detailed science talk, but more just going to highlight the geology changes that have happened over the past year. If you want to hear about the seismic gas or deformation parts of the eruptive history of the past year, please come back every Tuesday this month, and those parts of the story will have their own video to share. There's some excellent information there, so please do come back every week. So what we'd like to talk about or start with is 2020. We had a water lake, and the big question on our mind was, what's going to happen when magma returns and lava reaches the surface? Because these lava and water are known to interact very violently and cause major explosions. And as you can see in the video, we ended up not having a major explosion, and there's a lot of steam when the lava first starts erupting. So why is that? It was certainly a concern of ours that this was a potential outcome when lava reached the surface again. But what happened is that if you look in the infrared image on the left, this is one of the first images of the first fissure opening, and lava is already pouring down around the old Halima'uma'u floor and into the water lake. And that ended up boiling off the water lake within 60 to 90 minutes. During that time, this fissure propagated across the old floor that is downdropped, and then there was a vent on the north side that also opened up. And this old floor of the crater, became covered within the first day of the eruption. Now, even though we didn't see violent explosions that were very large, we did see a few minor steam and ash bursts from the eastern end of the lava lake over here. After it had replaced the water lake, there was still some gas that could come through and rip crust off the lava lake and produce small amounts of ash. We did see one of these plumes go over the road, but it didn't have any extra material that wasn't already being produced by the fountains when we checked the road for the deposit. Now, this video shows the north fissure after the lava lake has significantly filled up and the Halima'uma'u floor block is gone. And we're going to see something really interesting in this video. As the lava lake continues to rise, it's going to shut down the north vent and drown the fountain out. And the western vent, which is higher in elevation, becomes more active and becomes the dominant vent for the rest of the eruption. Now, in this video, you're also going to see that lava had started to go back into the north vent, and you can tell by the convection pattern. Now that daylight is breaking on this video, you can see that the material coming in from the west is actually pushing material up on the eastern side and causing a reverse convection. So as this video loops a second time, I'll point that out again, and you can see that. What's also interesting is that this island raft, as it approaches the northern vent, that's also around the time that vent shut down. And once the vent shuts down, it stops approaching the northern wall and it backs off and goes back into the center of the lake, which is really interesting. These floating islands are not unique to this eruption. Dr. Jagger saw them when he first started HVO in the lava lakes that he used to watch. So here again, you can see lava flowing into the north vent briefly, draining back down, and then now you can see there's kind of a line here where material is coming from the eastern wall towards the center of the crater and also from the western wall from the vent. And so we have kind of a upwelling convection on the east side. This is what's called a passive lava lake, where material flows in from the outside and then it has nowhere to go, so the material, as it's molten and remains fluid, can convect around, and that's what all these different plate patterns are showing us. Now we have a few still image panels of showing that island raft moving, because it's kind of hard to see in the video. This is the initial raft on the first day of the eruption, and as the next couple of days progress, it moves significantly north in the lake towards that north vent. When the vent shut down on the 26th, it did back off, back into the center of the lake, and as the west vent started feeding more material, we think that material helped push the raft towards the west vent over here. In early January, it did actually get really close to the crater wall, and then it backed off, and this ultimately did a 90-degree turn. So this area of two peaks on the north side of the raft in this December 30th image ended up facing the west vent by the middle of January. This is the total deposit eruption map for the December 20th eruption. It lasted until May 26th and was a total depth of 226 meters or 740 feet. The deepest part of the lake is right here in the center in this brown color on the west side. The total area here outlined in blue is 45,000 square meters, which is 111 acres. And if we were to cut this this map in half, we would have a cross section from west to east, where this dashed line is the old pre-2018 Halemaumau crater floor and caldera floor. The white line is the downdropped block area, and this lower section is the old Halemaumau crater, or what was left of it. And then in here we've drawn this orange line to show how much of the crater got filled by this December 20th to May 26th eruption. It's a total of 40 million cubic meters, which is about 10.5 billion gallons of lava. The peak effusion rate was 110 cubic meters per second, which is 29,000 gallons per second. And that's what these two plots here on the bottom are showing us as the total volume and then the eruption rate dying off. Most of the higher eruption rates we saw in the first 3 weeks, and by day 20 it had tapered off to a more consistent 3 to 5 cubic meters per second every day for several months. So this plot only shows the first 2 months of the eruption. We had a few months of quiescence, and then again on December 9th, December 29th, we had another fissure open up in Halemaumau crater. It started off with this north-south oriented fissure right in the middle of the lake, right on the east side of that main raft that is now rotated 90 degrees. And we ended up getting another fissure on this west side very shortly after this video ends. It was above the western vent of the previous eruption, but basically in the same area. As you watch this video, you can see the lava overtops the old lake surface, and some of these islands that were previously formed get buried. What was interesting is that through October, those rose up, and so there's a buoyancy issue going on here that was very interesting to document, and we're still trying to understand more about it. Another interesting thing that we observed in October and November, and even now in December, is the surface of the lava lake has a slant to it, which is a little interesting. So fluids usually make a very flat surface, and this is fluid rock. But if you are standing here at the observer, this is an image we would typically show at our staff meetings, showing all the measurements we make. A lot of our updates come out giving an average number or a single number, but in this particular image, it really highlights how much the lake is slanted, the lake surface is slanted. From the observer's view, they measured the lava being 327 meters below them on the eastern end of the lake. But in the center of the lake, it was 7 meters closer to them, so higher in elevation. And then near the vent, it was 313 meters, so another 7 meters higher. So there's a 14 meter, which is roughly 50 feet, 49 feet of difference, elevation difference between the west end of the lake and the east end of the lake. And this is over, that distance is about 7/10 of a mile or 1.1 kilometers. And that's a pretty big elevation gap. So this is what we call dynamic ponding, where the material and the viscosity and the yield strength of the lava basically pools up here. It's very much similar to how if you pour syrup on a plate or your pancakes, it makes a blob first and it has to spread out. And so at the end of the first eruption, we did see the lava lake kind of correct itself, and the east end rose up and the west end sunk down a little bit, because all of this is fluid under that solid crust that we see. And that will probably happen again whenever this eruption ends. But at the moment, there's anywhere from an 8 to 10 to 14 meter difference in the east and west elevations. We're going to zoom into the far right part of that former photo, and this is another downdrop block that recently had some overflows start to flow onto it on November 15th. And that, again, the western vent area here on this left image is about, in this photo, about 10 meters higher than where the overflows are happening. So there's a bit of a hydraulic or magmastatic head, if you will, that will help ooze this lava out as the crust continues to rise above the level of this block. It'll be a while before this one gets buried. This is a very large block and is also inclined, so it won't be as easy to bury as the one that got buried the first night of the first eruption. So in summary, the current eruption, which is still ongoing, has already erupted almost the same amount of volume, 38 million cubic meters as opposed to 40. So it's another 10.5 billion gallons of lava into Halemaumau crater. It's added an additional 60 meters of depth, which is at just under 200 feet, and the surface area has expanded by 52 acres. The peak effusion was 129 cubic meters per second. and that equates to 34,000 gallons per second on the first day of the eruption. That has also tapered off to an average of 1 to 5 cubic meters per second for most of the eruption. So here's that plot. This is showing the diffusion rate dropping. In both cases, it dropped within the first 20 days and maintained a low steady state. And the orange line here is the 2020 eruption. The red line is the 2021 eruption from September, showing the volume accumulation. Again, this is only showing the first 2 months of the eruption. The 2021 obviously goes on for longer. In the map here, you can see the outline in red of the current eruption and the current lake surface, and in blue, you can see the May or end of May, early June outline of the first eruption's lava lake surface. And so the difference between these two lines is that 56 meters that was added, 56 acres that was added to the surface area. So sometimes these numbers are hard to comprehend, and my colleagues at the USGS did a fantastic job making a visual that helps you understand what all these numbers mean. And so they compared the Empire State Building to our lava lake right here at Kilauea's summit in Halemaumau crater. If you were to place the Empire State Building at the bottom of the crater, you can see here where the water lake would have risen to on that building. This next orange plane between it and the top one is where the first lava lake ended in terms of the first 40 million cubic meters. And now we have another lava lake surface here that is actually a little outdated. It's from October 5th, but it shows just how much more volume has already been added with this eruption. It's actually, the overflows are right here. So this is actually, several meters higher than what this picture depicts. But this is an excellent graphic to help comprehend the sheer volume of lava that has been erupted this year. Now, the current activity, if you'd like to see it, you probably can, but it's in kind of this on-again, off-again quasi-steady state. So previously it was steady state, but low level, but constant. Now we've noticed that with the tilt and the deflation-inflation events, it seems to turn off and come back on. And this lasts a day or two, and this line is kind of arbitrarily drawn across the DI events, but essentially at the bottom of the DI event, the lava seems to go away for a day or two, and then inflation will start, and then we'll see lava come back as the inflation recovers and the pressure recovers. It doesn't happen on some of these smaller ones, but it has happened on these three bigger ones that the red line crosses. And as I was making this PowerPoint presentation to share with you guys today, you can see we had started a deflation, and by the time I ended up recording this presentation, the lava was already gone. So it'll probably be gone for a day or two, and then if inflation starts again, it should come back in a day or two. And we're expecting to see this pattern for a little bit, but one of these could be the last time we see lava until the next eruption. So just stay tuned, and if inflation comes back, then the lava should come back as well for now. All right, with that, I will say thank you very much. It's been a pleasure to share the first Tuesday of Volcano Awareness Month with you all. And if you have questions, please email us at askhvo@usgs.gov. Please come back for other future talks by the other disciplines, because they will be covering these same events, but from their perspective of seismicity, gas, and deformation. All right, have a great one, everyone.
All right, Dane, that was the first presentation by Carolyn Parchetta there. Some cool stuff. What'd you think?
Yeah, definitely. Be able to get, it's good to be able to go through it again in that kind of concise fashion with all the data being so, available now. At the time is, always harder as to look back and even just a year, or even at this eruption that's still ongoing. We did. Oh, sorry. Go ahead.
Go ahead.
I was saying we did have one question, I believe, but what were you going to say?
Oh, I have some notes of what I thought was cool in there, right? I mean, it was interesting she started off with the explosions, like the no explosions. We've talked about that in the past too. She did reveal that there was a period of increased activity of more vigorous spattering and bubble bursting and that kind of thing that lasted after the lake boiled off. That was kind of interesting. We hadn't heard that detail before. Right. It was interesting to hear that the whole recap of the north vent drain back, right? To actually see that time lapse and we've seen that time lapse before on where we had like one image per 15 minutes. We actually saw it like with images every second or so, every minute or so. So it's really a better time lapse. It's pretty cool to see the changes in circulation pattern on a crust that we we had followed but always wanted to see more, and finally we got a little bit more there. I find it interesting that they're using this term of passive versus active lava lakes, right? Yeah,
that is interesting.
The first one filling from above and most of the gas going up and away, that's the passive, right? And then you could argue that the eruption happening now might be more of this active lava lake style, where it's coming up underneath and through the bottom of the lake, right? We're seeing the whole top crusted over in between.
Well,
there.
The thing is with this one, it kind of transitioned because it started out on the wall, right? And then it eventually got up to the point where it buried it and rose up. This one's weird.
Yeah. But the lava reached the base of that fissure within 4 days of eruption beginning. So right. It may have drowned it. I mean, let's say it could have built up and lasted a couple more weeks. It's still been drowned for a long time. It's been mostly drowned, more time drowned than not.
Yeah. The one thing that I just came back to was that very beginning, that the explosion, or the thoughts around that. And as we saw and we've talked about previously, that this eruption, or the eruption in 2020, it came up through the bottom of it didn't come up through the bottom of the lake itself. It came up on the side and then poured lava down into it, which is very similar to what we saw in Green Lake. When Green Lake in the Kapoho crater was evaporated in 2018, lava poured in from the top. It evaporated all the water out, no explosions. My question is what happens if it comes up directly underneath that lava lake, instead of coming up right beside it and pouring in, but right under it? Is that the difference?
Yeah, and imagine gravity. Pulling all that water down into a crack that's trying to put lava out would not be the most passive.
Yeah. And you could get weird pressurizations in there and create situations where you could get explosions, I would believe. I'm not guaranteeing it, but that still seems like something that just leaps out to me is, that interaction. There's some dynamic there that makes it go explosive. Not sure what that is still. And hopefully maybe Don is the guy to talk to about explosive eruptions at Kilauea, so maybe something more in that speech as to relating to this.
I mean, that one's more of the deposits you can see around here, but he has talked about that before, and really he puts forth that it's the long-term magma supply rate, right? So when a rate is higher, that's when you can have the magma rising more quickly after a time of low magma supply, right? That's when you might have that interaction. Is what's been
right.
Interesting.
Definitely. All right, ready to get into the... Oh, I think we did have one question. We should...
hit me with the question, and I got some more observations too.
Okay. All right, so Richard asks, when the magma breaks out around the edges of the lake and the lake drops 40 feet, can the pressure drop be enough to cause higher gas releases?
Higher gas releases.
Yeah. So out around the edges and the lake drops 40 feet.
It's the pattern we're seeing is the opposite of that. We're seeing that the gas releases are what's pushing the lava out, right? So this is where I come back to my analogy of the eruptions being kind of like a bottle of champagne or soda pop, that kind of thing, right? It's like you have the gas under pressure dissolved in liquid at depth. Once you pop the top off, then the gas wants to escape, so it's rising. And as it rises, it forms bubbles, and those bubbles expand as they rise, and so it kind of rises and expands, and it eventually gets to the top. And all that liquid stuff that's just caught around a bubble just gets thrown in the air because the gas is trying to get out. It's really about burping the volcano. And once the gas is out, the lava will drain to the lowest possible place, whether that be that pit of the passive lake, or sometimes it's a fissure to drain back in a fissure, neighboring crack. It's basically burped to that point. The lava's gone flat, and you don't see more, you see a reduction in eruption rate from that point forth. That's what you usually see. And that's the pattern we're seeing with deflation-inflation events now, is when the lava is bursting forth, that's when the gas values are the highest. And when the lava is receding away again, you're seeing the values drop down to the hundreds of tons per day, which is like essentially non-eruptive values. So, maybe there's some other process that we can consider there on a localized scale, like where, one part of the lake here or there, as it's cooling and contracting, might be able to have more releases. But as a whole, the whole thing as it's measured, where the gas is what drives lava coming out, the gas output is much higher when lava is coming out than not.
Right. One of the other things I was looking at was just that caught me was the amount of volume that's been erupted between this eruption and the previous one. What was it, 38 and 40, I believe?
Yeah. So that talk was the first one, and I believe she recorded it at the end of last month. So we're up to, as I mentioned earlier, we're up to 40 million now, right? So 40 versus 41 is about the same.
Right.
Both over 10 billion gallons, right? So we're over 20 billion gallons total.
Yep. It's a lot like that last eruption, even in volume and everything.
Yeah, interesting. I mentioned that when I was pointing out my graph, like that initial value peaks, it was something we don't have that time resolution, but she provided the peak value. She said 2020, the maximum rate was 110 meters per second, and in 2021, 129. So pretty similar, but essentially a little bit above 100, right? It was the ballpark of. We're close. I think our estimate from the maps was around 90 something, but really it's around 100 there, right? And so 29,000 gallons per second or 34,000 gallons per second is the maximum rate. And it's gone down considerably. It's maybe like 5% of that now at most. You heard her talk about those values there. And I should correct myself. She did point out 14 meters is 49 feet, right? So that's when we saw the lava lake draining 13 meters in our plot earlier. That's probably 45 feet we're talking about, not 30 feet as I estimated earlier. That's how big that canyon is. It was filling in about 45 feet or so, I guess. The buoyancy thing is interesting. They keep coming back to that. They keep expecting the lava to just overtop that crust, but it keeps rising on them, and they are not satisfied with their I suppose hypotheses of how that might be happening. It seems like we haven't heard much about the details of how it might be happening or why, right? Only that clearly it is happening.
It is interesting, that whole thing, that it's lifting up the cap. It's easier to do that than to flow out of the open hole that it has sometimes.
Yeah, it really is. Yeah. So I mean, I think in my mind, just intuitively, I feel like there's got to be some kind of foamy layer, right, of like lava foam, like more gas-rich, bubbly stuff that's collecting top, and like that's like at the base of that crust, and like so you have some real variations in density, right, and something that would be really hard to tell without having more samples of the rock, that kind of thing. Interesting to consider that that's still a pending issue, right? That buoyancy thing. It was cool to see the map of the different depths, different points on a crater, right? That we haven't seen that presented that way before. We don't, as she said, the updates will usually only give one value close to the west vent, but it actually showed. Let me see if I can find that. Oh, there it is. Went right to it. This image where you see 287 over here.
Yeah, that was cool. That
314, 295, 320, 319. All the different spots they're measuring on here. You really get that tilted lake surface difference. That's fascinating. And then the fact that it actually righted itself when eruption was over, and then when the next one began, it retilted, and she expects it to rewrite itself after this one's over as well, right? So that's that kind of variation that's just talking about, and that's where our not point speculation of whether this could actually happen during a big deflation-inflation event in a 3-day pause. During 3 days, can you start having that thing start to tilt back before the next surge comes back and lifts it? So is that crust actually doing a seesawing kind of thing as lava's coming out, then it's not, then it's coming out, then it's not. That's fascinating, right? Like a little wiggly tooth kind of thing. I thought that was pretty cool, right? And yeah, that's really it. Yeah, the last thing is her statement that one of these pauses could be the last time we see lava until the next eruption, right? So I mean, she would not be surprised, it seems, if any one of these DIs is the last one.
I'm surprised it's still going each time it restarts. Like it's at that point for me. Like it feels like it's right there, and just feeling type of thing. But
right,
we saw as that last one is it could just continue on, even with no emissions, barely any pressure, barely any activity, but still lava.
Yeah, and this one has had more emissions, more consistent output. That's reached a larger volume faster. It's reflecting the changes in the deflation-inflation. So have we switched? It doesn't matter if it's an active lake versus a passive lake. Doesn't mean that the gases are able to mix into that area beneath the cap more so. Does that change the dynamics? How long it might actually last? I mean, I could easily go the other way and say like, oh, it's going to go on for another 10 years.
Right. It goes into another question that we just got through. It's asked, does seismic activity, the recent activity, indicate that this eruption will escalate, or do we not have enough data to say so?
There's not enough data. It's not clear if that deep those deep earthquakes are part of that deeper supply, or if it's more of an adjustment at the base of the volcano. It could be both. But in any case, we usually expect seismic activity that would anticipate an eruption to be shallower within the magma reservoir areas of the volcano. That would be in the range of 3 to 5 kilometers down and not 10 to 15. So the earthquakes are too deep. They're in a different part of the volcano. It's not exactly the plumbing system of it that's connected to the surface most directly. So I lean towards a no there. And if it will lead to some escalation, we'll see seismicity in the shallower parts of the volcano before that actually happens. And so until that happens, I'm going to go with no.
All right. Well, I think that does. We can get into the Olivine time capsule.
All right, Olivine time capsule here. Let's find it a little bit. And we'll be listening to Kendra Lynn, geologist.
My name is Kendra Lynn, and I'm a new research geologist at the Hawaiian Volcano Observatory. My research focuses on using the chemistry of rocks and minerals to better understand how, when, and why Hawaiian volcanoes erupt. For Volcano Awareness Month, I wanted to talk about my favorite mineral, olivine. It's actually very common in Hawaiian rocks, so anytime that you're out on a hike and you look at a lava and you see these little green minerals, that is the mineral olivine. Now, olivine is one of the most common minerals on our planet. In fact, we think that most of the interior of the Earth is made of this mineral. But it's also very common in Hawaiian lavas, and using olivine, I can learn a lot about the magma history, where it moved, how it was stored, and what happened to this magma before it erupted at the surface. Another cool thing I like about olivine is that if anybody has a birthday in August, the birthstone for August is called peridot. Peridot is the gem quality variety of the mineral olivine. So all you August birthdays out there, this is your mineral. Olivine is a relatively simple mineral. It's primarily composed of iron and magnesium atoms. And we can measure these compositions in the minerals using a variety of different techniques. So part of my job is to be out in the field collecting samples, but perhaps a bigger part of my job is to be in the lab. We can look at these minerals using a scanning electron microscope, and that actually tells us a lot. We can infer how hot the magma was, so we can get temperature with this iron and magnesium measurement. And changes in these iron and magnesium contents also tell us a lot about time. So we can actually look at changes in the chemistry to think about how long the magmas were sitting inside the volcano. When we measure the composition of olivine, we are often working with our partners at the University of Hawaii in Hilo. They have a scanning electron microscope, and we can take our samples and use that instrument to map all the different elements that are present. Most of the time we try to study phenocrysts, which is just a geologic term for a crystal that's typically greater than 0.5 millimeter in size. And these phenocrysts, which are kind of larger minerals, those are primarily only olivine. So after we go out into the field and we collect a sample, we usually bring back a bag that's sort of a mixture of fragments of older rocks, some fresh lava, or we call it juvenile material, and then in this bag are also olivine crystals. Using the microscope, we can search through this mixture of material and pick out the olivine crystals that we can then study. And ultimately, after we pick our crystals, we will polish them and mount them so that we can put them in instruments. And this is one example of an olivine mount. These are Keanakekoi olivine, and they're mounted in a metal disc that's then been coated with gold. And so each one of these little shiny surfaces that you see, each one is an individual olivine crystal. And we've cut them in half and prepared them for the instrument. One of the techniques that I'm really excited to apply in Hawaiian volcanoes research is called diffusion, diffusion chronometry. Each individual crystal is like a little stopwatch. It's a time capsule of information, and if we know how to read the chemistry correctly, we can get at how long the magmas were inside the volcano before they erupted. This map is one example of what a Kilauea olivine looks like when you measure it with an electron microprobe. We're looking at the distribution of iron in this olivine crystal, and you can see based on the color changes that there's more iron in parts of the crystal compared to others, and there's kind of a gradient between them. In this case, I would make a measurement between the core of this crystal and its rim and use that information to think about the timescales of this magma storage process. These olivine crystals from Kilauea's December 2020 eruption have force-straight zoning, shown as dark gray cores with light gray rims in these scanning electron microscope images. Most December 2020 olivine crystals have modeled diffusion times of about 60 days or less. And this suggests that the crystals, which originally grew deeper inside the volcano, moved up to a few kilometers or less than 2 miles below the ground surface about 60 days before they erupted. At that time, in late October of 2020, HVO detected the first set of earthquake swarms during the period of unrest leading to the eruption. These olivine crystals show that the earthquakes were due to magma intruding shallowly underneath Kilauea's summit. There are also some zoned olivine crystals from the September 2021 eruption that are being modeled right now to calculate the timescales from these most recent crystal clocks. Using diffusion in olivine is actually a really important tool for us because it helps us to understand eruptions that occurred prior to any scientific monitoring. So we know that Kilauea is a very dynamic volcano with lots of effusive eruptions that characterize sort of our historical past. But before that, Kilauea was actually quite an explosive volcano during the period that we call the Keanakekoi tephra. Most of these eruptions, especially the Keanakekoi tephra and other prehistoric explosive periods, they occurred prior to the arrival of Western visitors to the Hawaiian Islands, and not many are recorded in Native Hawaiian oral tradition. And so we have very little scientific monitoring data, and we have very little observational data that tells us what these eruptions were like. We're hoping that we can use the mineral chemistry to fill in the gaps of this knowledge so that we can have a better understanding of what was going on at the volcano during these times. As an example, what Olivine is telling us about Keanakekoi is that the plumbing system, the magma reservoirs beneath the surface, was actually very different at Kilauea during this explosive time compared to the modern effusive period. From the timescales modeling, we know that magmas during Keanakekoi were coming in from deep into the shallow parts of the system and mixing with other stored magmas. Now, these mixing events were occurring anywhere from a few weeks to a few months prior to each eruption. And so using this information, we're getting a better understanding of how the volcano evolved over this 300-year period of mostly explosive eruptions. We want to keep looking at these prehistoric eruptions to learn as much as we can about them. We also want to apply diffusion chronometry on Mauna Loa eruptions, and we can also use these techniques on Hualalai and other volcanoes in Hawaii. Overall, we hope to get a better understanding of how these volcanoes evolved long-term, over hundreds, maybe thousands of years. Having a better understanding of how Hawaiian volcanoes have evolved over centuries and thousands of years gives us a better idea of what future hazards might be if the volcanoes start to erupt in this different explosive style.
Mahalo, Kendra. That was the Olivine
Yeah, definitely.
talk there. What do you think, Dane? Olivine time capsule.
Yeah, the Olivine time capsule. I mean, I think it's very cool research, and I think it's going to really go a long ways into telling the story of how things, how these eruptions change and the differences between them, and kind of like the way to really track, these different nuanced changes that are taking place underneath the surface that we can't see. the mixing of magma as between shallow and deep, and the correlation with the explosive phase in Kilauea's history. That is definitely interesting, in that there's been so many. The explosive eruptions really are, one of those things that just we don't know the answer to exactly. We have hunches, hypothesis, but getting that where you feel the explanation is sound. I'm not quite there yet on everything, and I don't think anybody is.
Right. Yeah. That really is fascinating. Right. In fact, it's not part of this talk, but at the AGU just last month, at the 2021, she did present the results of that, and she basically hinted at it right there. Right. It's that deeper source is more unique than the one we're seeing now. It seems like it's coming from somewhere deeper where it would require, much more ascent, right? But it's still mixing with the shallow stuff, similar to now. It's just a deep component. It's a little different than our, deeper thing that we had now, for example, that came in December 2020 instead of 2021. That diffusion chronometry is really interesting, right? That each eruption, that they can actually see how long it's been mixing by measuring the rim and the core and the difference between them, and trying to calculate how long it takes for that. That's really fascinating stuff.
Right.
In hindsight, going back to October 2020, right? That's telling us that October 2020 intrusion underneath the campground at Amakani Payo was actually that earthquake storm was actually an intrusion, right? That's what she's saying. She's saying that was what corresponds to the cores of these olivines. So interesting that if we see at the time, we're wondering, are these earthquakes adjustment between Mauna Loa and Kilauea? Are they more of a Kilauea summit thing? And then the answer is in hindsight now, it was Kilauea pushing, right? So when we see that spot flare off again, we can probably assume there's magma coming into the system once again, to the point of stressing it, right? Just like we saw that upper southeast rift quaking, we saw it like as well. That's an interesting hindsight observation there, I thought.
Right, and it just makes you wish that you had these kind of data sets going back for the previous eruptions over the modern history, right? 1924, 1840, going back into the 1790 phase, even. Just it really is interesting just to have all these samples and what has been done in that, and it's only going to get more robust.
Yeah, so of course we can't get the earthquakes from then, but every olivine crystal and a lava flow has got some of that data within it. So that's what's cool, is you can learn something about the 1924 by going and looking. So that's really cool. Talking about that before, there was a volcano watch maybe a couple months ago that discussed this as well. We showed the pictures, so we won't belabor this one here unless you got anything else to add. I'll move on.
No, I think that's it. What we got next is a year of earthquake activity of the island of Hawaii.
Yep, here it is. Dr. Ninfa Bennington.
Hello everyone, I'm Ninfa Bennington. I'm a volcano seismologist at the Hawaiian Volcano Observatory, and today I'm going to be talking about the seismicity that has occurred across the Big Island over the last year. To begin with, let's talk about the three major regions where seismicity distributes across the Big Island. So first, there's Mauna Loa Summit and its southwest and northeast rift zones. Kīlauea Summit and the associated eastern rift zone. And then there's the Pahala region here, where we have both onshore and offshore events. Let's start by talking about Kilauea volcano. The 2018 eruption completely drained the lava lake that existed within Halemaumau crater. Following that eruption, we were left with the building of a water lake within the crater, shown right here. Then in December of 2020, we had a new eruption begin and the rebirth of the lava lake within Halemaumau. As we got into spring of 2021, the eruption quieted, and you can see here a dramatically cooled lava lake. However, in September of 2021, we had the resumption of eruptive activity and continued building of the lava lake. And as I talk to you today, we're seeing a period where we have pauses and restarts to this ongoing eruption. So the eruption might start again and the lava lake continues to build. Then we have these pauses where the lava lake cools, and we seem to be alternating between these two behaviors. Let's start by talking about the seismic activity that's been occurring at Kilauea Summit since the start of that December 2020 eruption. So first, we're going to look at the summit earthquakes that have been occurring there with depth. So here, each of these open circles represents an earthquake occurring at Kilauea Summit, and you can see them all across this profile. So our vertical axis shows the depth that these earthquakes occur, and we're going from 2 kilometers above sea level all the way down to 10 kilometers below sea level. Now the horizontal axis is showing time. So this red line here shows the onset of that 2020 eruption. And then as we move across this horizontal axis, we're progressing in time towards the time when the eruption quiets in the spring of 2021. The big takeaway here is we have the start of the eruption, and with it, the occurrence of all this seismic activity, all these earthquakes occurring shallowly within the summit of Kilauea. Now, as we progress into the eruption, we see that seismicity quiets. You can see here there's a real dramatic drop-off in the number of earthquakes occurring with time. Now we start to enter the spring of 2021, and we see the resumption of this seismic activity. We see more earthquakes occurring than were occurring before when the eruption was most active. And we see all this seismicity occurring, and the volcano continues to quiet and to cool, and then we get into the end of that eruption. Movies and TV have popularized what seismic data looks like when it gets recorded. So here in the left panel, I'm showing a classic seismometer, and it's recording these wiggles here, which are reflecting the amount of ground shaking going on in a particular place. And if that's big ground shaking, you get high amplitudes to these wiggles, small ground shaking, and the amplitude of those wiggles diminish. So folks are kind of used to looking at wiggles and thinking of them associated with seismologists. But actually, seismologists like to look not only at this sort of amplitude of wiggles, but also look at the frequency of the seismic data that we collect. So in the right-hand panel, I'm showing frequency data. So we're taking some window of these wiggles, and we're looking at them with frequency. So let me take you through these plots a bit. This vertical axis here represents the frequency of seismic waves from low frequencies, so starting at above 0 and going all the way to 20 hertz. The horizontal axis, again, represents time. So we start at time 0 for some time window we're looking at, and we go all the way to, in this case, 60 seconds or a minute out. Now I'm showing 3 kind of popular cases for the types of seismic data that we observe in the frequency domain. So if nothing's going on, there's no earthquakes occurring, there's no eruption, a lot of times what we see is this top panel here. So we have this bright orange and red color indicating that our strongest seismic signal is occurring here below about 1 hertz. And this will just continue on if there's nothing happening geologically speaking at the volcano. And that energy below 1 hertz is simply due to the crashing of ocean waves on the shore or the interaction of ocean swells with the ocean floor. So kind of the ocean hum going on our little island. Now what if there's an earthquake that occurs? Well, on top of this ocean noise that I just talked about, we get this energy arriving with both low and high frequencies. And you see here it kind of looks like this triangle shape. And this is the arrival of an earthquake at the summit of Kilauea. So besides those 2 kind of fingerprints to activity that's going on at the volcano, what else might we see? Well, during an eruption, if we have fluids moving within the shallow system at Kilauea, we often see these low frequency signals around 5 hertz and below. You see this orange and red color here. And that represents something called volcanic tremor, or the movement of shallow magma and other fluids through the shallow system within Kilauea Summit. So in this way, the volcano leaves different sorts of fingerprints that we can look at and identify to know what kind of activity is going on at Kilauea Summit. So now that folks have a basic understanding of what kind of activity is associated with a particular frequency domain, I'm going to start to show you the pictures in the frequency domain of the seismic signals we've recorded since the onset of that 2020 eruption. So first, let's look at the signal in the frequency domain that we recorded as the 2020 eruption started. And like that figure I showed you in the last slide, you see these high energy seismic signals arriving at about 5 hertz and below. And if you recall from before, that was something called volcanic tremor, and it was associated with magma and other fluids moving through the shallow system at Kilauea summit. And that drives really well with the onset of the eruption that we see here. So if we see these sorts of low frequency signals occurring, we often then look to other data streams to see if the volcano is erupting or inflating, any sort of indication that magma and other fluids are moving around and there's some sort of volcanic unrest occurring. Now let's look as we move into the eruption. We see the persistence of the most energetic seismic arrivals happening in this sort of tremor band. So again, fluid and magma is moving in the system. And then if you recall, with the resumption of earthquake activity in the spring of 2021, we had the start of quieting and cooling of Halemaumau crater and the end of the eruption. And you can see with that, we lose that volcanic tremor signal, and our entire picture, what we see come about, is that ocean noise and nothing else. So we can actually really chart the eruption and the associated activity by looking at our seismic signals in the frequency domain. Now let's talk about volcanic activity that has occurred since the end of the eruption that began in 2020. So since that eruption's end, we've had the resumption of seismic activity or earthquakes occurring at Kilauea summit. You can see here as we're moving with time away from that eruption end. And if we look in the frequency domain, we see that that high energy seismic signal at frequencies of 5 hertz and below has disappeared. So we no longer have that volcanic tremor signal. And that makes a lot of sense, because if we look at Halemaumau crater, we can see there that it's obviously cooling and eruptive activity has ended. Now, of course, we also had this September of 2021 eruption that occurred, and we see here this large amount of seismic activity that occurred right as the onset of the eruption happened. And then following the onset, similarly to the 2020 eruption, we see that seismicity really started to dissipate dramatically as the eruption went on. And if we look in the frequency domain, we see that we have the appearance of volcanic tremor again, indicating fluids and magma moving shallowly within Halemaumau. And we can see that similarly in the picture here, where we have the resumption of building of the lava lake. And so that's where we're at right now. We have this ongoing eruption going on at Kīlauea, and as we've had pauses and resumptions in the lava lake activity, we've had both the appearance of the volcanic tremor and then moving towards an absence of the volcanic tremor and sort of going between those two behaviors. So that sums up what's been going on at Kilauea in the last year. Now let's move on to the Pahala region, where we've seen a real change in annual rates of seismicity. If we look in this left-hand panel, I'm showing just a week of seismicity occurring in 2013. And in 2013, seismicity rates in Pahala were pretty low. So here I'm showing just a week of seismicity. This is generically outlining the Pahala region. You don't see a ton of events. This figure in the top panel is showing weekly counts of seismicity. This vertical axis shows the weekly counts, and the horizontal axis shows time. So you can see in 2013, the amount of earthquakes occurring was pretty low relative to the amount of earthquakes that you see as you move later in time. Let's move to 2017, or even let's look earlier. You can see that by 2015, relative to earlier years, we're starting to see an uptick in the number of earthquakes occurring per week in Pahala. And I'm showing here this middle panel. This shows a week in 2017 of seismicity on the island. And so you can see here, I'm just sort of generically outlining the Pahala region. But again, seismicity is slightly increased relative to the distribution of events happening in this region in 2013. But the real jump happens in sort of mid-2019, and you can see the number of events being counted in the Pahala region really starts to take off to dramatic levels. So if you see here in this right-hand panel, this is just a week of seismicity occurring in Pahala in 2021. So it's an extensive amount of seismicity. So what could this swarm or high number of earthquakes occurring in Pahala mean for the region? What could it represent geologically? There was an interesting study done in 2015 by scientists at the USGS where they postulated this very question. And they looked at not only those earthquakes occurring, but they also identified tremor, similar to what I was talking about earlier at Kīlauea, but at this time occurring within the Pahala region. And this tremor was located deep, about 40 kilometers below Pahala. And as I talked about earlier, it's often associated with the movement of fluids and magma. Now, right above this tremor that they located were all those Pahala earthquakes that I was showing you in the previous slide. And when you plot those and look at them with depth, they form a nice linear chain. You can actually see even better in this figure above, moving towards Kilauea. And they hypothesized that this region represents a mantle fault zone towards Kilauea, where perhaps these magmas and fluids move towards the region and perhaps even act as a source for deep magma into Kilauea. Of course, this is currently a hypothesis, and permanent stations that HVO has in this region are fairly sparse. If USGS can densify the number of stations or seismometers within the Pahala region, at least temporarily, we can then start to image the structure of the subsurface in this region in order to better understand why we are having all of these seismic events. And so that's a future project happening with the USGS, likely beginning this spring or summer, where we'll be placing these very small seismometers densely through the Pahala region, collecting data for a few months, and then using that data to model what the subsurface in the region looks like, so that we can try to better understand what's going on at Pahala and the reason for these swarms of earthquakes. With respect to island-wide seismicity, let's finally look at Mauna Loa. In spring of 2021, it produced seismic swarms. Those are most easily seen if we look at this plot of earthquakes per week. Again, that count's going to be on the vertical axis versus time. So in the spring of 2021, we have these upticks in weekly seismicity, and that went down following the spring to these lower rates seen here as we march in time to the present. These swarms plotted in two regions. Here, across Mauna Loa summit, with this northeast-southwest trend, and then also a second region of events, here located immediately west of the summit. And these are two common regions where we see seismicity, whether in a swarm level where we have lots of seismicity occurring, or just kind of weekly low levels of seismicity. Following these swarms, though, we've gone into this period of very low activity at Mauna Loa, with not much going on. Finally, we move offshore to Luihi Seamount. This newly named submarine volcano is located immediately east of the south point of the island of Hawaii. And in the last several weeks, it's had a swarm of seismic events occurring there. This culminated in a magnitude 4.9 event in this region. And these events may represent either the intrusion of magma and fluids into the volcanic system there, or volcanic activity. At this time, due to the fact that we're observing these events from our network of onshore stations, we can't differentiate between the two. This concludes our summary of seismic activity across the Big Island for this month's Volcano Awareness Program. Thank you very much and have a wonderful day.
All right, Dane. What do you think?
Yeah. So the big thing that immediately jumps out to me is back down in Pahala, right? And it's interesting that they're going to be deploying that mesh network of seismometers down there to be able to better get some better data out of there. But the thing I'd really like to see is she's talking about the deep tremor and coming up to the decollectment fault, which is labeled here the mantle fault zone.
Those are different things, actually.
Oh, different things?
Yeah.
Okay, sorry. But anyways, the thing I'd like to see is that lateral flow at 40 kilometers. If they're detecting tremor beneath Pahala, then if it's a transport region at that depth, then we should be able to see the fluid moving through there. We should be able to see a tremor of some kind. It seems like she mentioned that they don't have that kind of very in-depth monitoring in that area, and that might be part of the thing. to do with it. But that's the thing I'd like to see come out of that, is that the area between Pahala and the Kilauea summit, to show that there's tremor between there. I think that would be big.
Right. But yeah, and then of course we've talked with Brian Shearer about this, and depending on the character of the conduit, you might not get tremors because of geometry as well. So that's something to try to pin down as well, right? But this study by Weck and Thalen in 2015, there's that same plot I showed you before. Let's see, pull that one back up. The reason I pull this up is because this piece of it up here, right? This is kind of similar depth of the plot as off to the side here, where they're actually showing the different characters and depths of mantle fault zone earthquakes, then a tremor earthquakes, and a tremor itself, all at characteristic depths underneath this Pahala zone. I can scroll it across here so you can see, right, where the yellows and the reds are there, right? So the reds is what they're showing as tremor. And you can see there's red dots all through here. There's a big cloud kind of all through here, but then you also see these red dots like all through there, right there. Not as many, but they are there. Just not as dominant as you see over the Pahala region. And some deep ones underneath Kilauea as well, as that you imagine that deeper source coming up, and then possibly one coming up this way, right? So yeah, fascinating. Yeah, it's
and also the not just to continue that thought. Sorry, to see if we can not only to Kilauea, but if there's tremor emanating out in other directions as well, potentially Mauna Loa or Loihi, right? Is this just feeding Kilauea, or is there something more to it?
Yeah, absolutely. Yeah, and since you bring up Loihi or Kamae or Hua Kanaloa, and I keep practicing that one, that perhaps that they can associate some of that earthquake activity that happened recently with that Pahala swarm as well. That'll be interesting to see in the future as well. But while I'm on that, that they suggest there was either an intrusion or an eruption down there corresponding to that 4.9, but unknown if that was the case or not, and kind of waiting more information. So, but yeah, the data is basically there. It's just not very accurate as far as like the drawing a shape around it, right? You couldn't say like, oh, this thing has got this kind of shape, because you just can't trust the shape of it with that low resolution. So I think what you might get is a better defined cloud boundaries, perhaps, right, from having that deployment, and that's what the imaging will really do for you.
That'd be good,
right? Just kind of like trying to look through binoculars, having that dual focus. So,
that's good to see that they're really putting some time and effort into that Pahala region, because I think it warrants it, and there's not really all that much happening elsewhere, so might as well figure out exactly what's going on there and if there's any implications for the future, or if it's just a outstanding event almost. But yeah, a little bit more information, a little bit more knowledge and communication would be good on that.
Yeah, and it's interesting to see this updated Pahala earthquake frequency plot, right? We saw one of these with Brian Shearer back in 2019, right? So that was before these two big peaks that came through, the first at the end of 2019, and 2020 was mostly going back down, and 2021 was the second peak, and we're still coming down from that one now. So really, it's it's been very noticeable. Like 2015 was noticeable. Like that change right there was big already at the time, and so it's really been 10 times bigger than that change over the last year. So it's cooking down there, and interesting to see what will happen next. But of course, to reassure people, there's no sign of any magma coming to the surface there or anything like that. So it's more of an academic curiosity than it is like a fear of anything coming up there.
Right. Yeah, they're very interesting stuff. And that Pahala area, just we've talked about so much, and still so much to be known about it. It's kind of one of those curiosity things.
Sure. And then just to wrap it up here on this one, we've recapped Mauna Loa quite a lot, but good to hear them saying the same thing, same plot. Mauna Loa has been quiet since the spring. Yeah. Anything else before we move on, Dane?
No, I think that's good for this one.
All right, so these last couple are a little bit shorter. We're going to hear Don Swanson speak here about the recent explosive history of Kilauea, right? So since the last caldera collapse, we're talking 1500 or so to 1800 or so, more or less. And this is a location that's kind of behind the water tank of the old HVO building, right? It's a place that anyone who's been lucky to go on some field trip with Don, or past years when Overlook was open, or did training through the park, or anything like that, would have been taken to the spot that he's kind of curated for a long time. So it's cool to see this immortalized. Without further ado, let's play it for you guys here. Don Swanson, only 3 minutes, we'll be back soon.
Hi, I'm Don Swanson, a retired geologist from the Hawaiian Volcano Observatory, and we're now at an outcrop near the old site of the observatory, which shows very nicely beds that were produced by explosive eruptions from about 1500 up until 1790. I've dug this deposit out to make it and added labels so that people can see the various types of deposits and the ages. This lower one here is a reticulite. Many people who live in Volcano dig down to reticulite. It's this loose, very lightweight material that is common throughout the village in most places. Then above that, there are several different layers. C is missing, but E is missing, and F. G is missing, but H and I and J, each with their ages appended. And this tells quite a story. Each of these beds is a chapter in a book that could be called The Explosions of Kilauea, 1500 to 1800. Each of these beds was produced by at least one explosive eruption. When the caldera was deep and water was mixing with the magma or with hot rock, and these explosions were quite violent. And some of the explosions were so violent, such as this one here, J1, that it sent an eruption column 12 to 15 kilometers into the air in 1790. This is an explosive time at Kilauea, 1500 to the early 1800s. There was another similar explosive period at Kilauea between about 1200 years ago and 1,000 years ago, between about 2200 years ago and 1,000 years ago. And this is the way the Kilauea erupts. It has long periods of time during which it's mostly explosive, and then long periods of time that it's mostly effusive, sending out lava flows. And this is a good example of one of those explosive periods.
All right, short and sweet, Dane. What do you think?
Yeah, it's really interesting to see him dig through those layers of ash. I remember when we went up there and we're looking at that area that, we weren't touching anything really, but to see him peel that away and, the dynamics with the tephra and stuff like that as well, just it really puts it all together. And one of the things I was thinking about is, how sometimes we refer to like the 1924 explosive eruption at Kilauea, and it's like it's a different kind of explosive eruption compared to these ash deposits that you see.
Yeah, 24 is notably absent there on top, right? If there's a layer on top, it's individual rocks and not enough to make a whole bed. That's really the
right
interesting thing there.
It's just a night and day difference between what we've seen, and people were talking in 2018. Oh, look at the explosive activity, right? A 30,000 foot ash column, right? It's like, no, that's not what we're talking about when we're talking about like the explosive phases of Kilauea.
Yeah. The one that sticks with me is a 790 eruption. Or, no, I guess it was just in 24, right? There actually was ash that collapsed the gutters in Glenwood at the Glenwood store, right? So
yeah, and that is a story, and it's been documented. And one of the things I've always talked about with that is like, okay, gutters in 1924 in Glenwood, what was their integrity like? What were these gutters held up by? How rusted were they? That kind of stuff. It's
for sure.
Hard to. Yeah.
And they certainly collect, like, it's collecting their ash across the whole roof, right? So like you're funneling it all into like one area, right? But still, like it's enough to actually collapse it, but not enough to leave a deposit on the surface. So that's kind of my point, right? So there's a lot of stuff missing from the geologic record. It's kind of similar with fossils, you only get what gets preserved, what's able to get preserved there. Not everything is able to get preserved or differentiated later on in time.
Right, and we did get a dusting of the ash and stuff in 2018, and just not anywhere near this kind of notable.
Right. Now that was something we heard was surprising at the time, right? You could never pick out that millimeter layer of ash, like in Pahala, from out all the other layers of ash there are there as well.
All right. Well, I think we're getting ready for the last one, yeah?
Yeah, last one. This is going to be Brett Carr talking about the structure for motion, three-dimensional mapping of Kilauea.
Hi, I'm Brett Carr, a geologist at the Hawaiian Volcano Observatory. Active volcanoes, like Kilauea behind me, are dynamic landscapes that are constantly changing their appearance. New vents can form, the ground can collapse forming craters, and lava flows can cover the mountain slopes. As part of our monitoring of Hawaii's volcanoes, it is crucial for HVO to measure these changes in the elevation or topography of a volcano that occur due to eruptive activity. One powerful technique we apply to measure these changes is called structure from motion photogrammetry. Structure from motion photogrammetry, or SFM, is a method that uses tens to hundreds of photographs from a digital camera taken from multiple perspectives to reconstruct the three-dimensional shape of the terrain in the photographs. This technique is based on the concept that it is possible to perceive the 3D shape of an object by viewing it from multiple locations. Our eyes and brain do this naturally. By moving around and viewing it from different perspectives, I can understand the size, shape, and location of this tripod without having to physically touch or measure it. It is from this motion that we are able to understand the structure of the object, hence the term structure from motion. The trick, until recently, has been teaching a computer to do the same thing. Software advances over the past decade have allowed for the rapid generation of topographic maps or digital elevation models from photographs. And now SFM is regularly applied by HVO and other volcano observatories around the world. Creating a new map of Kilauea's changing topography begins with taking the photos. Airborne photos work best, so HVO geologists use a helicopter or a drone to fly over and around an active crater or lava flow and capture photographs from as many perspectives as is safely possible. The photos are then loaded into the software and processed to create the digital elevation maps. How frequently we conduct these overflights to take photos and make new maps depends on the eruption. For very large and hazardous eruptions, like in the Lower East Rift Zone in 2018, helicopter or drone flights were conducted and maps made nearly every day. For smaller and less hazardous eruptions, like those within Mauna crater over the past year, we will do a flight every week or two. During an eruption, maps need to be produced quickly to inform both HVO scientists and the public about ongoing activity. At HVO, we have focused on streamlining the SFM processing such that if there is a helicopter overflight in the morning, we can produce a map later that same day. A great benefit of SFM is that it gives us this ability to choose the frequency, extent, and resolution at which we make maps so that we can be flexible to the data demands of the eruptive activity that is occurring. There are many things we can learn from the maps produced by SFM. First, they show where the lava is and where it isn't. By comparing a new map to a previous map, we can identify what has changed during that time period and calculate useful information such as the volume of lava erupted, the eruption rate, the surface area covered by lava, and how fast a lava flow is advancing. Conducting multiple overflights, creating multiple maps, and calculating a series of these measurements allow us at HVO to better understand how an eruption is evolving over time, what are the current hazards, and when an eruption might end. Working with other scientists at HVO with expertise in earthquakes, ground deformation, and lava and gas chemistry, we can combine our data sets to learn more about the magma plumbing system and how changes inside the volcano relate to the eruptions we see on the surface. In this way, SFM photogrammetry is one of many powerful tools HVO applies to monitor and study Hawaii's active volcanoes.
Yeah, Hello Brett, that was the last one. I think.
Very interesting stuff. I was just thrown off at the end by that one of the devices that they were looking at into the crater, that big looking like a telescope looking thing. It only flashed up for a frame, and I'm trying to pull it back up, but
yeah, that one right there, yeah, pretty... MIDAC. I think that's that might be possibly the gas measurement, right? We're looking at that red source. Not sure.
Yeah, I like being able to see some of the just them processing stuff and the program they're using and stuff like that. It gives a little behind the scenes of some of the stuff that HVO does on the regular to produce these maps. And that one, yeah, that's.
Then there's this map they put up with a trimmer at the different stations. So you get a little bit of a peek at their internal displays here. That would be nice if they expanded their public offerings. Center.
Yeah, because they got a lot of this stuff and really, well developed stuff at HVO. It's just some of it's not available for us to be able to see online.
Yeah, but they do put out quite a lot of stuff, right? Including all these talks. It's interesting to see that what they do put out, even though we didn't get these graphs, for example, like for a while. Like we have these exact same graphs produced from their maps. They put out. Right? And we come to it's interesting. See how their work is all falls out, so we can still use it and share with you guys some of this more educational content here. Yeah, pretty cool.
All I know is that man needs a mouse, because doing all that kind of work on a trackpad, ooh.
Yeah, hopefully that's just for the
display
film shoot.
Photos
here,
are then loaded into.
Hopefully that's what it was.
Yeah, very cool stuff.
All right, so there is one thing to mention. We can see if there's any questions about any of these talks here. But one last thing to mention is there was a Volcano Watch erupted today. Not erupted today. A Volcano Watch issued today.
It works.
Getting late here. It's one of our longer updates in a while.
Yeah.
But gratitude for the University of Hawaii partners. So we won't read through all this, but there's the Center for Study of Active Volcanoes, CSAVE, and RCUH, Research Corporation, University of Hawaii. That helps with all the measurements of. So I won't read through all this, but you guys can be posted. But you can see all different integration of staff that exists there, right? And it was actually even mentioned during the Olivine talk about why you there. That's the last thing there, and we got any final questions, Dane?
No, that would be it. Definitely. We'll be coming back next week with another more normal update with whatever the changes are on Kilauea and Mauna Loa. And if anything happens that we need to come on live, we will do so.
Yeah, for sure. Yeah. So thank you guys. If you haven't yet, please like, share, subscribe. And till next week, unless something happens in the interim that's worthy of us jumping in as usual, we'll plan to be back with you guys next week, Thursday. And until then, for Hawaii Tracker, he's Dane DuPont. I'm Philip Ong.